You can't comb the hair in a coconut. It's called the hairy ball theorem. Let's prove it. First, because it doesn't matter, let's trim all of the hair on the coconut so that it's the same length. Now, to prove the theorem, we're going to assume that it's not true, that you can comb the hair on a coconut, and we're going to show that that's impossible. If that's the case, at each point on the coconut, the hair at that point points in a particular direction along the coconut. Importantly, the hair is combed smoothly, meaning that nearby hairs are pointing in nearby directions. No cowlicks. So first, I want you to consider how the direction of the hair changes as you go around the equator of the coconut relative to the direction that you're traveling in. For example, imagine that as you go around, initially the hair is pointing in the same direction as you're traveling, but it sweeps out a full circle clockwise relative to the direction of travel. We would say that the rotation number is 1. If it swept out 2 full circles, it would have a rotation number of 2, and if it swept out a circle counterclockwise, it would have a rotation number of -1. Now, it's important that the rotation number is always a whole number, even if it winds around a bit, goes back, and then goes forward, because it always ends up back where it started, so it must make a whole number amount of turns. Also, you might notice that because the hair is smoothly combed, the rotation number around any closed loop can't change as you move the loop around just a tiny bit. It's a discrete number, so smooth transitions can't cause sudden jumps. So if you start to tilt the equator, no matter how much you tilt it, the rotation number about the tilted loop can't change. In particular, if you tilt that whole equator 180 degrees, you get the same circle, but now it's in the opposite orientation. So the rotation number of that equator is the negative of the rotation number of the original equator. But if the rotation number is the same, that means that the only allowed rotation number at the equator is 0, because 0 is the only number that's the negative of itself. Now we can also drag that equator up to the North Pole, so it's just a tiny little loop going around the top. Now because the hair is smoothly combed, nearby hairs point in nearby directions, and so if the loop by the North Pole is small enough, effectively all of the hair on that tiny loop points in the same direction. So as you travel around the loop, the rotation number is either plus or minus 1, depending on which direction you move around the loop. Basically, the direction of the hair is fixed, but the direction that you're traveling in makes a single circle. But now we have a contradiction. According to the equator, the rotation number for the whole coconut should be 0, but near the North Pole it should be plus or minus 1. But smooth transitions can't change the rotation number, and yet a smooth transition must have changed the rotation number. This is a contradiction, so that means that an assumption that we made was wrong. Namely,